Venga, ahora sí, ya puedes empezar.
Okay, so I'm going to make it in English unless someone's got some problem. So this is the defense of my thesis entitled Generation and Exploitation of Intermediate Goals in Automated Planning. My advisors are Daniel Borrajo and Susana Fernandez. We're going to go through these points here, some small introduction about what planning is, then 3 main lines of research, and at the end, some conclusions. For those who may not know it, I think everybody does it here. Automated planning is about finding a plan, a sequence of actions that allows us to get some goals from a given initial state. So this is the formal definition of planning. It's a tuple with a set of propositions, the actions of a problem, the initial state, and the goals, right? So this is a small example of a typical planning task in which you have to load packages in the truck, then move the truck to G, and then unload all the packages, right? So that's a sequence of actions that can be parallel, that may not be able to be parallelized, whatever. So under this premise, the main problem with planning is that it is domain independent, which means it is pretty hard p-space in the worst case. This means that the search trees are usually exponential, and one of the main approaches to solve this problem is to try to split the problem into smaller several ones, like we humans do, right? So if we want to get to our jobs, we first go to the car, and then we drive our car to the parking lot, and then we go from the parking lot to the office. And this is kind of the main motivation of our thesis, right? So we're going to try to come up with domain-independent methods to split this problem. So there are 3 lines that have quite a bit of a relation between them. They're not separated. But still, we're going to make it like a third and a third and a third of the thesis. The first one is regression, in which several subsections. One of them is revisiting stuff that has been done in progression for its use in regression. Then symbolic search and invariance, and then some technique called backward goals, right? Then we're going to switch, and we're going to go to random sampling and planning and implementation of a randomly exploring rapidly exploring random tree in planning, and then last but not least, the landmark graph and how to solve its problems and how to exploit the information it gives, right? So first of all, we're going to go to this first subsection here. In this case, the main motivation is that heuristic search was proposed in 1999, which is 15 years ago. And at first, it was possible to search forward and backward. Experimentally, forward worked much better. And that's why most people just gave up on researching our regression and took progression as the only way of solving this problem, right? However, after all these many years, we now have a much better understanding of the problem. We have a broader set of techniques that work in progression. And yet, regression is not dominated by progression, right? One of the key things here is that, for example, there are some benchmarks that are really bad for progression that are thought of as traps for forward-chaining planners. Another thing is there's a huge gap in terms of how regression works, right? The understanding is much worse. So what we're going to do here is to come up with, revisit some techniques, propose some novel ones, and maybe not, generalize a few things that were not really well defined, like reasonable orders, right? So I'm going to go into detail about how these things work. I'm just going to mention a few of those here. So for example, we get backward searching subplans, which is a more natural approach, and it contains some constraints. So it's more informed, right? We also propose disambiguation of states and actions using state invariants like mutexes and invariant groups. For those that may not know it, mutexes, 2 propositions that cannot be true at the same time. For example, me being here and me being right there. I can't be at 2 places at the same time. So that's a mutex, right? In this case, we can infer additional information, prune spurious states that can't be detected as spurious when using only mutexes. Reasonable orders in regression, most people said they were unsound. They are sound but only in regression this allows us to infer some pruning methods. Applicability with the deletion. In this case, we thought of HSP, which check mutexes individually. In this case, we avoid the generation of spurious states altogether by modifying the applicability of actions in regression with the deletion, which is quite neat. Regarding reachability heuristics in regression, in regression we only had HAD and HMax. However, with more general caching schemes, we can actually compute every single reachability heuristic, like the FF heuristic, which is the one we want to compute most of the time. And also, we can cache, for example, best supporters to compute preferred operators for regression, which wasn't possible before, right? The context-enhanced heuristic is a bit special. We proved here that the caching scheme works also in DTGs, and computing this heuristic is still efficient, right? And also for the selection of the pivot, we can use reasonable orders to get a clue, right, or some ideas on how to get them. And last, we have heuristics in P2, which are not practical at all to compute. Those are much more informed than the original heuristics computed in P1, but they are not practical to compute per state. However, in regression, we can use same caching schemes to compute, for example, the FF heuristic in P2, which, and the time is still linear on the length of the real X plane. So this is quite nice, actually. The main thing that came up from this work was a new planner called fast downward regression, FDR, that tries to behave better than HSPR, which is its predecessor, right? Built on top of fast downward. And in this case, the experimentation, we are going to try to see where regression places, right? So small table here with the number of problems solved per domain. These columns. First one is fast downward in progression, no preferred operators, FF heuristic, grid best first search. Second one is the same thing, but in regression with the FF heuristic. Third one, FDR add, is with the add heuristic. Fourth, with the context and haste additive heuristic. Then FDR2 is with the FF heuristic, but computed in P2. And the last ones are HSPR, the original backward search planner, and MP, which is Madagascar, which compiles the problem into a SAT instance and performs regression on it, right, to try to solve it. So in this case, we can see that still progression is better. However, if we do a per domain analysis, we see that, for example, there are some domains like floor tile in which regression works much better. And yet, HSPR is not able to solve the whole set of problems because some techniques, in this case, is disambiguation, the one technique that makes the difference, right? As we can see, for example, FDR2 is able to solve all the problems in Park Printer, which the other planners can't. So we are seeing here that in terms of also looking at the totals, as we can see, HSPR is dominated by fast downward regression because these techniques actually do matter, right? So right now we could say that FDR is at least in backward search the best planner compared with HSPR. So we're going to go into another subject, which in this case involves optimal planning. The solution must be optimal. This symbolic search, in which we work with sets of states instead of working with individual states. And this is done by using binary decision diagrams, right? So these BDDs allow to sometimes get exponential gains, both on size and on time. It uses extensively regression, yet most of the techniques that were deemed as really important in explicit search weren't proposed for its use in symbolic search. So that's what we're going to do, right? For those that may not know it, this is the decision diagram. So at every single variable represented by a node, there's a true and false path. And to know whether a set belongs to that set, we go down the path until we get to the true sync node, which would mean the state belongs to a set, or to the false node. If we look at the example here, this is a BDD that represents 3 states. The first one is obtained by following that path down, and the second one corresponds to this one here. The third one is this one here, right? So pretty easy in theory, not so much in practice. So in this case, what we're going to do is to make a BDD that represents all the states that would be pruned by using state invariants. So mutexes, those are just a conjunction of two propositions, two fluents. In this case, is the disjunction of all the conjunctions of those fluents, right? Furthermore, we can encode the constraints of the invariant groups by using this clause here, and everything together is CBDD, which is a single BDD. It may be several BDDs, right? But usually it is a single BDD that can be used to prune spirit states from our regular BDDs. So for example, if this is a mutex, like V1, for example, is maybe in here, V2 is maybe in somewhere else, both true can come here. This is a state that normally would be pruned by using mutexes. If this is our set of states, then we can see that by computing the difference with CBDD, we actually go there, and this path that came to this subgraph here goes directly to the false node, which means that this subgraph can be pruned, right? This is not so, this is the best case. There's a negative case also in the thesis for those that may be interested in it. But this case, for example, would mean we'd get an exponential gain in size, right? That's not the only thing we can do with CBDD. We can also use minimization algorithms that allow some spirit states in the BDD to be represented, and that may lead to smaller BDDs. We can also encode the constraints in the BDDs that represent the operators, the transitional relations, and not so much with CBDD, which saves us one operation, the difference. And also we can use these constraining symbolic techniques for abstraction heuristics, which use a lot of regression too, and get strictly better estimates, admissible estimates. So this is a table that, again, shows the number of problems solved in this set of domains. Gamer, which is the planner we built these techniques on top of. This is the vanilla version, right, with no mutexes. CGamer is the one that uses CBDD, and the difference, CGamer O is the one that encodes the constraints of our problem in the operators. And then we get the winners of the IPC 2011 competition, which is LMCAT Core Planner and FDSS Stone Soup as a portfolio. So as we can see here, Gamer is not bad at all, right, from the very beginning, coming from work by Alberto Ralba. However, we get much better coverage in pretty much every single domain, right? Some domains there are no additional constraints, like elevators, yet we don't lose problems, right? And comparing it with LMCAT, for example, which is a single core planner, the difference is certainly there. So right now, CGamer, as far as I know, is the best performing optimal planner. So bidirectional blind search, by the way. This is the algorithm that we're trying to do to use in this case. So really good results in here. Now, third part of the first part is backward generated goals, right? This comes from the idea that the relax plan that comes from the computation of FF heuristic give us much more information. And for example, helpful actions prefer operators. That's critical in the performance of many, many planners, forward chaining planners, right? So in this case, we came with the realization that the last actions of our relax plan are usually the same, and those could be exploited in the same way, right? So what we're trying to do here is regress using those actions to get meaningful backwards goals generated backwards that allows us two things. First of all, enhance the forward heuristic, and second, try to halt the search before it gets to the goal, right? Because it's kind of like bidirectional search to some extent, right? So in this case, this is a small example of regression, right? If those 4 dots there, circles, are our goals, if we have some action A1 that adds one of them, if we regress using A1 over that set of propositions, then we'll get this whole set of propositions here. And in a regular domain, if we compute relax plans forward, we'll get, at the end, some actions that can be used to regress. Some cannot, right? because there are some constraints. Those actions must be applicable, for example, in regression, for them to be able to be selected as the action chosen to generate this BGG, right? So also it is interesting to see that, to realize or note that the regular reachability heuristics already deal with multiple goals. There's no change whatsoever. It's just, like checking action applicability, because action applicability is a set of propositions that must be true for the action to be applicable. So that's just like checking whether a goal has been fulfilled or satisfied. So if we look at this picture here, these waves are the layers, the G layers of the relaxed exploration that stop whenever BGG is found, and then the relaxed plan is obtained from that BGG. We could use, for example, this action here to generate a new BGG there, right? If the heuristic yields 0, which means the state satisfies a BGG, then we can stop the search. No problem whatsoever. In this case, we're talking about the percentage of solved problems from these sets of domains. First one is Java FF. Second one is BGG on top of Java FF. We're using both heuristics. Both of them use prefer operators or helpful actions in these cases. As we can see here, for example, this gold miner domain, here there are strong constraints at the end of a problem. It's kind of a trap for forward chaining again. We go from solving half of the problems to solving the whole set. And overall, we get a better coverage. Also, that's the ratio of the expanded nodes by both planners. And we can see we tend to expand much fewer nodes, right? So again, good news. Now we're going to switch a little bit and go to another main line of research. In this case, what our motivation comes from the fact that even though forward chaining planners behave quite well and are really the best performer out there, they have still some drawbacks, right? Some shortcomings in the sense that, for example, they are really sensible to transpositions. They may fall into local minima if the heuristic is not informed, right? And these are things that actually happen in planning quite a lot. Whenever a domain is hard for these kind of problems, it's usually because of these reasons. So ideally, we'd like to have some search algorithm that would be more robust, right? Be able to recover from these local minima, that may be incremental, that may keep several options open in case one of the options is not a good one. So what we did here is to adapt these rapidly exploring random trees that come from motion planning to automatic planning, and we call them RPT, random planning tree, right? So these are trees that alternate sampling and expanding towards a random state in the search space and going towards a goal, right? So if you want to know how these trees look like in this tree that's been built, so essentially we sample some state here, and we extend a little bit the closest node. And that extension is the one that gives us a new branch in our tree, right? Main advantage of these kind of trees is that they are biased towards unexplored areas, because these are the Voronoi diagrams, right? The areas of the search space that are closest to one of the nodes that come from the tree, right? So as you can see, unexplored areas correspond to bigger Voronoi regions. So the odds of sampling a random state there are higher, which means that in the end, we get Voronoi regions that are more or less of the same size. Whenever that happens, that means that you're covering your search space quite well. Now, the problem with this is that random sampling in an implicit search space as plannings is not at all trivial. It's pretty hard, in fact. And what we do here is, instead of trying to prove that a single state belongs to the search space, which is as hard as finding the solution of that subproblem, we use the same state invariants, mutexes, and invariant groups here to rule out states that cannot belong to this search space, right? And this is done by turning this problem into a CSP, constraint satisfaction problem, in which the variables are the invariant groups and the constraints are the mutexes. This is not as simple as CSP in many domains, by the way. We can get lost solving these problems. We use heuristics from the CSP literature. Now, this tree is characterized by having two parameters. First of all, as we mentioned before, sometimes we expand towards a random state, sometimes we expand towards the goals. This is determined by this p-value, right? And there's also another parameter, which is the maximum number of nodes that can be expanded during the local search. So we don't over-explore some given area that might not be interesting for us, right? So say, for example, we sample here this state. We find out that this Q near is the nearest state. And then we expand towards it with a given limit. And if we can't reach Q rand, then we generate the closest node from our open list, which is Q new, as a new node of our tree, right? Again, if you want to see what the real advantages of these are, is, for example, in this case, this is the heuristic, right? If we use a forward chaining planner, and this is an obstacle here, that's an H plateau that must be explored until, this is like a basin flooding phenomenon. However, if we sample towards some random state that is actually useful for our planner, then instead of spending all this time here, we're keeping both options open. And then eventually, if we realize that this one is the one that we need to find a solution, we will expand from then on from that Q rand there, instead of trying to search the whole plateau. So again, number of problems solved. Fast downward is fast downward with greedy vector search, preferred operators, FF heuristic. These are base planner too, right? Because we use a base planner for these local searches. Llama, winner of IPC 2011. And these numbers here, these are all RPT configurations. This is the epsilon, number of nodes, 10K and 100K. And this is P, right? So basically, these three here do smaller searches. Those three there do bigger searches. This means most of the time it goes towards some random state. Most of the time it goes towards the goals, right? As we can see here, these are selected domains. First, we're going to look at the total row. In terms of coverage in this large set of domains, we actually get better coverage than Llama and much better than FD, which is the base planner that we're using for local searches. This, of course, is different depending on the domain, right? In this case, for example, these domains are known to be hard for forward chaining planners, and we get much better coverage for all the options, right? Barman, because of how it's defined, it is impossible. There are plenty of dead ends that are unintended, and in this case, we don't get meaningful mutexes, right, from the H2 computation, which means that we are often sampling spurious states and going towards there, which can be seen here in the sense that more small searches are worse than few bigger searches, because you tend to expand more, to explore more, and whenever you sample spurious states, the search effort will be wasted. In this case, this is the same domain, Sokoban and Sokoban learning from the learning track. Those are not identical. First of all, the definition of the domains are not the same. And second, the structure of the domains are completely different. In this domain here, the density of solutions is low. There are really few options to solve a problem. In this case, it's the other way around. There's a small constraint at the end in the sense that we have to find a good order to push the boxes. But there are plenty of options to solve that problem. So as we can see here, the lower the density of solutions, the worse RRTs tend to behave, which is kind of expected to happen, right? And the opposite phenomenon also occurs. So this really gives us a clue of what kind of domains might be better for this RPT planner to work at. And here, this is another case in which we can see that Llama is able to solve all the whole set of problems because of the heuristic, Llama count heuristic, which here behaves as a goal count heuristic, which is really good for this visitor problem, which is in fact a trap domain for the FF heuristic, which explains why FD behaves so bad. This one doesn't use the good heuristic. It uses the bad heuristic, yet it is able to solve many more problems than its single search counterpart. So again, good news in terms of results. And for the third part of this presentation, we're going to go and take a look at the landmark graph and landmarks in general, right? So these landmarks are the hot thing, well, one of the hot things right now in planning, and they've been used really successfully by several planners like Llama, and this landmark cat planner, which was the winner for core planners in the IPC 2011, also was based on landmarks, kind of. However, I mean, these landmarks are represented generally by the landmark graph, but this has several shortcomings in the sense that, for example, techniques that exploit the landmark graph ignore cycles, ignore negative effects, don't take into account mutexes between the landmarks. So that got us wondering whether there could be a more interesting alternative, right? I'm going to highlight the problem of this landmark graph here by using this small example, which is called the Sussman's anomaly. This initial state, and we have some robotic arm here. I didn't paint it, I don't know why. Our goal here is to get A on top of B and B on top of C, which means that we have, at the end, we have to have some kind of tower A, B, C, right? So this is the landmark graph for this problem. And now we realize, for example, say we're going to split this problem using the landmark graph into several smaller ones. So the next step would be choosing to solve a subproblem whose goal would be either clear A or holding B. But we have no clue about which one we should obtain first. So we use our planner, and somehow, because of how ties are broken, we actually get holding B. And this is wrong. This is wrong. This is not the good option. However, we have no way of determining whether this was a good one or not. So now that we have holding B, we could, for example, achieve on BC because all the previous landmarks are satisfied. And then we get this tower here, and now one of the goals is satisfied, right? However, this goal must be undone for the whole tower to be built again. So all the effort that we made achieving those landmarks that are now achieved is wasted. And now we choose again clear A, right? And we are given again two options, whether get holding A or do other stuff. In this case, B on top of C is already achieved, so you don't really consider it, yet that's a good option. So say, for example, we go for the unachieved landmark, which in this case is holding A, and now we do, again, wrong things. And this goal must be undone to obtain the whole thing. So a problem whose solution's got 6 actions, its optimal solution, now it's got a bunch of them, and we wasted a lot of effort. Imagine with a bigger one, right? And this is because we are not taking into account these orders, negative effects, cycles, and so on, right? So our motivation here is to try to find those things that are really represented in the current formulation of the landmark graph by computing alternative characterizations of this graph. We propose 2 ways of doing this. First one is encoding it into a SAT problem and solving it. And the other one is make an abstraction out of this landmark graph, which can be solved by regular domain-independent planners, right? So yeah, we're going to go with the second one, SAT compilation of the landmark graph. Now, this also came from the realization that landmarks are propositions. And these edges are constraints, right? So it's really the same thing as the planning graph in the sense that we have positions, and we have some precedence constraints, state invariant constraints, and so on and so on. The main difference is that the planning graph encodes, apart from actions, of course, time, and this mutex is per level, which is really interesting. So in this, we're going to do the same thing as SATplan does in case somebody here doesn't know what SATplan does. It turns the problem, given an horizon n, for example, into a SAT instance and tries to find a solution in there using a SAT solver. So given a horizon, encode it as a SAT problem and solve it. So we're going to do the same thing, but using clauses from state invariants and the landmark graph, and propositions only from the landmark graph instead of using the whole set of propositions of a problem. So A and B are landmarks in these clauses. Init is the first level at which a landmark can be achieved, which corresponds to its H max value. And the number of time steps, the horizon. And T is the time step at which we are generating the clause, right? So there are several clauses, existential clauses. All the landmarks must be achieved at some time in a given problem. So these are straightforward, right? Landexes, which are a generalization of mutexes, these clauses enforce the fact that, for example, I cannot be at the same time in two places. Or, for example, say we got holding A and holding B. Those are mutex because we only got one arm, right? But in order to achieve holding E from a state in which holding A is true, we need two steps. We first have to put down A or stack it on top of another block, and then pick up B, right? So that's a Landex of two. And those clauses can be encoded in our set instance so we don't get states that violate them, right? Now, these ordering clauses are obtained from the landmark graph. These are all the precedence constraints. I'm not going to go into detail, just you should know that this means, for example, if some landmark must be achieved before another one, this is the kind of clauses you should use before encoding it into a set instance, right? So if we go back to our example here, the soundmass anomaly, I have put the landmark graph this way. We're going to set a horizon, in this case six time steps. Turn this landmark graph into a set problem as we just described, and then use a sub solver to solve it. And in this case, for example, there are plenty of interesting things in this small example. One of the main characteristics of this block-roll domain is the fact that the arm must be used consistently, right? So arm empty because true and untrue at every other time step, right? So all the even time steps have arm empty as true. All the even time steps, all the time steps have arm empty as false. These are the goals of a problem, and in this case, we are seeing that those must be true at the end, and this one must be kept from this time step on, right? So this is one of the most important things. First get this one, then get the other one. And now we got the rest of the landmarks, which actually tell us which one we should achieve next, right? If we try, for example, to get clear A at the first step, the only action that performs that is unstacking C from A, right? So okay, I'm going to show you. Well, it doesn't really matter. So unstacking C from A. Remember that C was on top of A, and then we got B, and that's the thing we have to do: unstack C, then put it down, then take B, put it on top of C, and then A on top of B. If we try to come up with actions that would satisfy these constraints here, those would be the actions. Only the optimal plan is able to satisfy these constraints. So we would require no search to find a solution for this problem, only working with a subset of the propositions, right? Now we're going to go into the last part of our talk, which is kind of doing the same thing, but with different motivations. So again, we face these problems of not having a really good sound order, total order. We also have, right now, no theoretical implications from the landmark graph. Okay, we got the landmark graph here, but what does that mean? I mean, does that give us some bound on the cost of a problem? We don't know. So what we're trying to do here is to turn this landmark graph into a planning problem so we can extract additional information from it. This is done by just considering all the negative interactions between the landmarks, all the actions that are achievers, and at the end we aim to have some problem that, after being solved, will give us, first of all, a total order, more informative, and then some clues on the bounds and the costs of our problem. So remember that this was our tuple there. We actually get the same thing, right? Only that in our PEF's problem, we only consider propositions that are landmarks plus additional propositions that represent whether a given landmark has been achieved, right? Because that's the kind of constraints we get in our lemma graph. As for the actions, we get those that are achievers of landmarks, and we keep the effects and the preconditions that are landmarks too. But we also want to encode additional negative effects that may not be evident just by looking at the action, and that's done by using deletion. Because in order to achieve some given landmark from another landmark, we may have to delete the first one by some action in the middle of the path, of every single path. So that's the thing that deletion represents, and in this case, we can capture that even if those actions aren't in our problem, right? So again, we will respect cycles. We will take into account that some landmarks must be reachieved, and so on and so on. As per the formal information that we can get from this abstraction, there are plenty of properties that are really related most of the time with the admissible landmark heuristics that are extensively used in optimal search. And well, there are some conclusions here. For example, this the cost of the optimal solution of our abstraction is an admissible estimation of the cost of the optimal solution in the original problem, which means that can be used as an admissible heuristic. And another important thing is that it is not bounded by the solution H plus there, right? The optimal cost of the relaxation of the original problem, which is bound on the rest of the landmark heuristics, except for those that are computed in P2, but that's a completely different thing. So if you want to know what these kind of abstractions look like, this the problem I presented before, just with a small constraint that the track can only carry one package at the same time. And by using this domain-independent method, we get an abstraction that looks like this, right? So in this problem, for example, the track at A is a landmark. The track at G is a landmark too, because you got to get the track to G before you can unload the packages, right? The packages in the track are landmarks too. However, there are several paths that we don't really care about in this problem. Those are not landmarks. We can choose to get to G by going through B and D or C and E or several options. So those are not landmarks, and those are taken away, and now we get new actions that take the track from A to G and to G from A, and this is more a problem, so it's easier to solve in theory, right? No more transpositions in that middle section there. So these are the costs of several estimations, depending on the number of packages in our problem. This is the optimal solution of our abstraction, H plus, and the optimal landmark counting heuristic. And as we can see here, for example, given 3 packages, which is a really small problem, the more packages we have, the higher the difference will be. In this case, we can see that H, the optimal cost of a solution of our abstraction is in fact higher than H plus and LM cat, right? And it's still much higher than the optimal landmark counting heuristic. So that's pretty much everything. In this case, we get much finer serialization of our problems. We have no disjunctive goals like this clear A or holding B in the Sassman's anomaly. Which one should we use? Now, in this case, we don't have those. We always have a sound course of action, right? It exploits cycles, includes all the delete effects and mutexes, can be incrementally computed too. And from an optimal search point of view, that's really interesting to use as a seed for another optimal abstractions, abstractions that aim to derive optimal heuristics, like merchant swing and this cigar, new cigar thing. So finally, some conclusions. 3 main lines of research have been explored. Those are related, even though it may not be clear. There are small things like all the constraints, for example, the same things that must be respected in the regression must be respected when doing this random sampling. And those are the things that the landmark graph lack, for example. Bidirectional search is also really relevant with RTs, and there are many things that must be taken into account. The results were good overall in the sense that, for example, for optimal search, we right now got best performer, at least from the results that have been published lately. RPT also is really good in terms of coverage. Really depends on the domains, but on large sets of domains, it's better than Llama, which is really good. And there are some sound relevant theoretical discussions that also contribute to the advancement of the state of the art. So still room for some future work. How bidirectional search works in satisfying playing, which has been analyzed in a paper that we just published. Some novel applications of these landmark characterizations, like, for example, using not forward chaining planners, but rather planners that look in the space of planes to divide the problem, and so on and so on. And that's it. Thanks for your attention. If you have some questions in Spanish or en español, o como queráis. Como queráis.